All right, we're going to be solving some exponential and log equations and then using them in some financial applications in section 3.6. So we're going to start off here with a couple of straightforward equations. A lot of these, or all of these, are going to require you to switch forms, to know how to switch forms. But we've been doing that a lot anyways. Some of them require you to condense. So you're going to be using the properties of logarithms that we covered in 3.4. The idea when you have an exponential function like this one is to get the power by itself and then to switch forms. So this one, the power is already by itself, so we're ready to switch forms into log form. So the natural log of 19 is going to equal x minus 2. Remember, the logarithm equals the exponent. So I'm going to add 2 over. I'm going to write a statement as often as I can. I'm going to try to write a statement that gives an exact answer. This would be the exact answer to this. I don't know what the natural log of 19 is, but whatever it is, plus 2 is our answer. So I'm going to go ahead and find out what that is approximately on my calculator. Natural log of 19, make sure you close that up, plus 2, it's about 4.944. So x approximately 4.944. Okay, I'm going to stick to the thousandths on these. And the next one, we have to isolate that 2 to the 3x first. So we're going to have to subtract 3, get negative 17, and then divide by 5. So a negative divided by negative is a positive. I have 17/5. I'm going to leave that exact for right now. And now we're going to switch forms. So our base is 2 this time. Just a little bit. So our base is 2 this time. Log base 2 of 17/5 is going to equal 3x. So that means that x is going to equal 1/3 log base 2 of 17/5. I'm going to go one more step here. And, somewhere along the way here, you could kind of skip one of these steps if you want to. But I'm going to make sure that I show my change of base formula. That we have 1/3 of log 17/5 over log of 2. There's my change of base right there. If we go ahead and type that in, and again, I hope that you write this, especially on the quiz or test. If you use the template that's on your calculator, that's fine. In fact, I'm going to do that. I'm going to take 1/3. Well, I'm going to just divide by 3. So I'm going to go alpha window number 5 is that template. So we're going to have 2 as our base, 17/5. I won't do that. 17/5 as our power, and then I'm just going to divide this whole thing by 3. So it's going to be about 0.589. I'm going to skip down here to a logarithm problem where we have to condense. So in E here, we have addition between two logs, so that's going to become multiplication within. So we can write x times x plus 21 if we want to, or we can go straight to distributing it. This is going to equal 2. Okay, here's the big step. We have to switch forms. Probably should have that in parentheses because that whole thing is within the logarithm. Our base is 10. So we're going to have 10 squared is going to equal x squared plus 21x. Okay, so if we were to show the step in between that, what it would look like is this. 10 is the base, the exponent is 2, and that will always equal the stuff that's in there, x squared plus 21x. But then I just change that 10 squared to 100. All right, so we have x squared plus 21x equals 100. X squared plus 21x minus 100 equals 0. This is factorable. X plus 25, x minus 4. So we have x equals negative 25 and x equals 4. And of course, we have to check for extraneous solutions. Remember, in a logarithm, this can never be negative. Must be or 0. It must be greater than 0. Must be greater than 0. Okay, so this negative 25, this is an extraneous solution. Our only solution here is 4. In the next one, we're going to condense again. This time we have division. So within one logarithm, we're going to have division. This becomes my numerator. This becomes my denominator. And it's going to equal 2. All right, so now I'm going to switch forms. Switching forms would have, this is my base. This is my exponent. 3 squared is 9. So we're going to have 3 squared equals x plus 4 over x minus 5. This is 9. I'm just going to switch this around. X plus 4 over x minus 5 equals 9. And then I'm going to multiply both sides by that denominator to get rid of it. So we have x plus 4 equals 9x minus 45. And I'm going to subtract x and get 8x. I'm going to add that 45 over and get 49. So x is going to equal 8/49, which is 6 1/8. I'm sorry, 49/8. We're dividing by 8 here. There we go. Which wouldn't be a bad idea to throw back in there. I at least know, actually, I'm going to just say that this is 6.215 just to get that number in my head, because if I go back up here, I just got to make sure it doesn't make anything negative. For sure, this doesn't become negative because it's going to be 10.125. This also is going to be positive, 1.25. So, you can plug it back in to make sure it is the correct answer, but at least we know that it's in the domain, so it's not an extraneous solution. All right, we're just going to set up and maybe complete a few here application problems involving finances. So hopefully you got this sheet handy, although these formulas are right on the notes there. But we're going to be using, our compound interest formulas down here on the bottom, which hopefully remember from Algebra 2. Using these, we're just going to be solving for a couple of different things here. So the first thing you want to notice is how many times your interest is being compounded. If it's annually, you're just simply using basically our growth formula right there. So whatever your initial amount is, you've got $5,000 at a 5%. We've got 2 people here investing. We got 5% simple interest and then 5% annual interest. We're just going to use this to calculate the Quan Lee's 5,000% or $5,000 at 5% annual interest. So $5,000. Our rate is, let's not put that. Our rate is 5%, so it's going to be 1.05. It's our growth rate. And we're going to take this to the 10th. Okay, if you're writing a model first, you'd call that T, but since we just want to answer how much it is after 10 years, we'd call that 10. And if you put that in your calculator, you get $8,144.47. We're going to round to the hundredths here because we're dealing with money. If you are compounding some other amount of time per year besides annually, when you are compounding monthly, daily, weekly, whatever it is, quarterly, we want to use our compound interest formula there. So we are going to take that $500 that Roberto was investing, 9% interest. It's 9% annual interest, so it's 1 plus, except this time we need to divide it by 12 because we are compounding it monthly. And we need to take our number of years and also multiply it by 12 because it's going to be compounded 12 times a year. Sorry, the number of years is 5. And I should probably have just multiplication. Let me clean this up a little bit. There we go. So the only thing that I ask that you do here is find out what this would be, if you were writing a model first. So like I'm going to take 0.09, divide that by 12, and I get 0.0075. So I know that this is 1.0075. And in fact, I'm going to treat this like a model first for any number or any amount of time. Because then what I'm going to do is I'm going to take this 1.0075 to the 12th. So let me just write this as this, just so I know that this is, oh, I didn't add. Let me go a second. Let's try this again here. There we go. Got that. I didn't add the 1. I got to add the 1. All right, now that I've taken 9% divided by 12 to get this 1 point, or the 0.0075, I'm going to add 1 to it. And I know that you know that adding 1 to it is just going to give us 1.075. But the reason why I'm having us do that is because I want us to find out what this is here. Maybe not particularly for this problem. For this problem, I'd be okay with you just putting 5 in right now and getting the answer. But I just want to show you something quick to relate this to something we'll be doing shortly. If we took the 1.0075 to the 12th, I'm going to rewrite this as 1.0938. I'm gonna round it there, but I'm actually going to store this on my calculator by hitting store, which it says then answer, and basically it's asking what do you want to store it as. So I'm going to store it as, it doesn't matter, I'm going to store it as A and hit enter. So I've stored that base as A. And the reason why I did that is because, or the reason why I found this is, what I want you to notice is this is basically in the form that our annual percentage, our annual compounded principal would be. So in other words, this percentage here, 0.0938 or 9.4%, is basically what our 9% compounded monthly is equivalent to. So 9% compounded monthly is about 9.4% compounded annually. So that's why compounding more often is better. It gives us a better interest rate. And for example, up here, when we just compounded at a percent annually, or I'm sorry, this one, we would have made more money if we would have compounded it monthly or daily even. The more you compound it, the more money you would make if the percentage stays the same. So let's go ahead and then throw 5 in here and figure out what this is going to be. So I'm going to take this value to the 5th. I'm going to multiply that by 500, our principal, and we're going to get $782.84. And the only reason I went through this is to connect this to the annual, or if this was compounded annually. That's what the percentage rate would be. All right, so now we're going to have $500 invested at 9% compounded monthly again, which we just found out before would give us that. I mean, if you want to start out by writing this, you can. This should be 12t. But we know that that ended up being that 1.0075. So we want to find out when this is going to equal 3,000. So that's going to be my amount. And we're going to solve this algebraically. You could graph and look for an intersection, but I want to go ahead and solve this algebraically. So we're going to divide by 500 first. And have 6 equals, I'm going to call this 1.0075 to the 12t. And actually, I stored this value on my calculator as A right up here. after I took that to the 12th and I got 1 point, I stored that as a. So I actually have that stored. So I'm going to change this then to 1.0938 and round it right here on paper. And I'm going to use the exact value I've stored in my calculator. Because now if I switch forms, I have log base 1.0938 of 6. That's going to equal t. But on my calculator, I have this stored as, just write like this, stored as a. So I know that I can take log base or log of 6 divided by log of, on my calculator, a, and it's going to give me the number of years that this will take. So, or you can just use your template on your calculator here to get that. So we've got log of 6 divided by log of the 1.0938, which I called a, alpha a, and we get about 19.983, or almost 20 years. Just over, or just under 20 years. So this problem had us finding time. The last type of problem that we're going to look at here, we're going to find what interest rate we would need to get a particular amount after a certain amount of time. So we're going to invest $500. We're going to try to double it. So we're going to get $1,000 starting with 500, doubled after 10 years. So we don't know the interest rate, so I'm going to leave this as R. We are compounding quarterly, which means we need to divide by 4 and then take this to the 4 times 10, so obviously 40. So what I want to do here is divide by that 500. We get 2 equals 1 plus R over 4 to the 40th. To get rid of this, we need to take the 40th root of both sides, or in other words, take both sides to the 1/40th. So I'm going to have that 1 plus R over 4 is going to equal 2 to the 1/40th after taking both sides to the 1/40th. And if you want to write that as the 40th root of 2, you can, but on your calculator, the easiest way to do it is to take 2 to the 1/40th. Then we're going to have to subtract that 1, and we're going to have to multiply by 4 finally. So I know that R is going to equal that 2 to the 1/40th. Then I'm going to subtract 1, and then I have to multiply it by 40. This is basically what I'm going to type in my calculator here. 2 to the 1 divided by 40. And we'll subtract 1, and then we'll multiply that by 40. We get R is about 0.69919, so about 7%. I'm going to leave it as, yeah, I'm just going to round it to about 7%. Okay, we have one more type of compound interest problem that we want to do, and that is when we are compounding continuously. As soon as you see the word continuously, you know you are using the PERT formula. We're not going to do it for all these different years. How about we just pick after 7 years? We'll get rid of all this. We're just going to find after 7 years how much is in this account. So we've got $100. If it's compounded continuously, you can't use, I'll go back over here. You can't use this formula if it's compounded continuously because there's no K value that represents continuous. So that's why we need E. All right, compounded continuously, we end up using E. So the rate is 8%. we are going to just find this after 7 years. So I can basically type this in my calculator. Just clear everything off here. Type this into my calculator like this. 100 times e to the 0.08 times 7 years. So that $100 after 7 years, if it's compounded continuously, is going to become about $175.07.